All right, hello everybody. We're going to go ahead and talk more about the periodic table. Now, a lot of this lesson is going to be review, but there's going to be some things where it's going to be new, but not hard at all. So let's go ahead and get started. Okay, so it took nearly 2 centuries to develop the periodic table we use today. Just like the development of the atomic theory, there were two main contributors to the development of the periodic table. Now, the first guy we're going to talk about is Mendeleev. And Mendeleev produced his periodic table in 1869. Now, again, he developed the first periodic table, and the way he arranged the elements were increasing atomic mass and and clumping the elements by similar properties. Uh, he also placed them in groups, and he used playing cards to create his table. He kind of like, okay, this card's gonna be this element, this card's gonna be this element. Okay, let's kind of maneuver it on a table and figure out how it's gonna look to organize the elements we know today. And he made blanks on his table for unknown and new elements. Now, in 1869, majority of the elements that we have on the periodic table today were not discovered or were not invented. So there was a lot of blanks in his table. So when he organized it, he created space for them. So when they were invented or discovered, he would go ahead and put the information onto that table. Now, this is what his periodic table looked like. It is vastly different than what we see today. And there's a lot of question marks, kind of like, oh, what do we think? But that is pretty much what his periodic table looked like. Then, after about 100 years later, we got Moseley in 1911. Not 100 years later, more like 50 years later, sorry. And Moseley developed more patterns among the new elements. At that time, 50 years later, that's a lot of time. There's a lot more elements that were invented and discovered, and a lot more properties were discovered as well with these elements. So he was able to create more patterns and more grouping for similarities and differences between each element. So with that, he arranged the elements to increase in atomic number and grouping in properties. So main difference between Mendeleev and Moseley was Mendeleev used increase in atomic masses, while Moseley did increase in atomic number. And he's the one who kind of started to develop the periodic table we see today. Now, Mendeleev and Moseley have the right idea to organize the elements based on their properties, but it worked out better with the elements' atomic number and order. So that's kind of like where Mendeleev went wrong in his organization. While Moseley was more on spot, it made more sense and more put together when you're organizing it by atomic number. Now, with this idea of the arrangement that we have today, it's called the periodic law. And this law is when physical and chemical properties of an element are periodic functions of their atomic number. So their atomic number increases, and as it increases, that physical and chemical changes are being changed or are developing as you increase or decrease the atomic number. Now, this idea helped develop the modern periodic table elements we use today. And as we all know, the periodic table is an arrangement of the elements in order of their atomic number, right? Their atomic number increases from left to right. So the elements with similar properties fall in the same column or group. And we're going to take a look at those groupings in a bit. Now, again, here's a periodic table. We see that the elements are increasing from left to right with the atomic number, and there are boxed in positions very neatly, and we're going to investigate those properties. But let's go ahead and talk about specific arrangements with the periodic table. Now, kind of like what I kind of talked about the past couple chapters with the word periods and groups, the periodic table is arranged by periods and groups. Now again, our periods are the rows on the periodic table, so left and right. They're the horizontal rows. And there's only 7 periods in the periodic table. And groups are the columns on the periodic table, the up and down, the vertical columns. And there's only 18 groups on the periodic table. So let's kind of like pick out some elements and figure out what group and what period they are in. So let's go ahead and look at carbon. Now carbon is in group 14, right? That number right on top. That group 14 is the up and down. So carbon is in group 14. Now carbon's also in the second row, so that means carbon is in period 2. Now let's look at sodium. Now sodium is in column 1, so sodium is in group 1. Sodium is also in row 3, so sodium is in period 3. Now let's go to palladium. Now palladium is in column 2, so palladium is in group 2. Palladium is in row 5, so palladium is in period 5. Then we got radon. Now radon is in group 18, so group 18 because it's in column 18, and is in the 6th row, so it's in period 6. It's kind of like what that idea of groups and periods are in the periodic table. Okay, so now I was talking about these characteristic groups, having these elements grouped up by similar properties. Let's go ahead and look at these groups. Now, since the elements are arranged by similar properties, the periodic table has 6 characteristic groups. So the first one is group 1 elements except for hydrogen. Now, all these group 1 elements, they are called alkali metals. They are very, very, very highly reactive metals. Moving on to all the group 2 elements, we call these the alkaline earth metals. These are also highly reactive metals, but not as highly reactive to like alkaline metals are. All right, our next characteristic group is the center elements from group 3 through 12. And these elements are called transition metals. Now, transition metals are very, very special metals, and we're going to talk about more about these later on throughout the trimester. Now we have these elements, these certain elements on our right side of our periodic table. And all these elements are highlighted in green are just regular old metals. They're not that important. They do some stuff, but they're not as important to get their own names. We're just going to call them just general metals. Then now we have these blue highlighted. It's kind of like a ladder in a way on the periodic table. And these elements are really unique because they're called metalloids. Now, metalloids take the characteristics of metals and what we're going to talk about next, nonmetals. And they have the same characteristics. They kind of just share. So they're kind of like playing both sides of whatever's a metal and non-metal. Then we get to these elements are highlighted in purple, and these highlighted in purple are called nonmetals. Just regular nonmetals, not too special, doesn't really get their unique name, but they're just nonmetals. Then we get to all of the elements in group 17. And all the elements in group 17, we call them halogens. Now, halogens are nonmetals, but they're very, 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 very highly reactive nonmetals. That's why they kind of get their own name because they're super, super, super reactive, super, super volatile. Then we kind of talked about this during electron configurations, but all of the elements in group 18, we call those noble gases. Now, they're also all nonmetals, but these noble gases, they are not reactive at all. They just kind of like want to stay what they are. They don't want to bond with anything. They don't want to chemically or physically react with anything. Just kind of just want to be left alone. They're very unreactive gases. Then we get down to our excerpt of our periodic table, and these are all elements from 57 through 71, and these are called our lanthanides. Now, majority of these lanthanides are not found naturally, but they are laboratory made, so it's kind of like a little bit uniquely, and they're more of the recent variety of elements. As well as elements from 89 through 103, we call these our actinides. And again, these actinides are recently founded, but they're also all laboratory made as well. So with all these 10 characteristic groups, let's kind of like dive into their similarities. Why are they similar? Why are they grouped up like this? And we're going to first talk about the alkali metals. Now, Um, Now, the alkali metals, they are very, very highly reactive to water. So here's a video of what I did couple years ago in class when I put sodium, so sodium is an alkali metal, sodium in water, just regular old sodium metal in water. As you can see, that sodium metal blew up into smoke, and you saw some of the sparks and those flames as well. So let's go ahead and talk about, okay, as I go down the alkanides, do they still react in water? And if so, is it the same explosion or is it bigger or smaller?
Whether you've left school or you're still at school, you can appreciate the sheer fun and mayhem that chemistry can be. There's so much to it. Bunsen burners, mixing chemicals. Very nice. Now, you may have been allowed to mix very small amounts of lithium with water. You may, if with a responsible adult, have mixed H2O with sodium. And you may, under very strict scientific control, have witnessed potassium mixed with water. But the odds are, if you have, it will only ever have been on one of those rubbish science videos. There you go, mate, present.
Oh, thank you very much.
These next two are the dog's nuts of the periodic table. They are, if you like, the king and queen of alkali metals. Mix these babies with water, stand well back, and watch the mayhem. And that's just what we're going to do. Mr. Tickle, bring on the rubidium.
Here it is.
Is that it?
Well, it might not look like much, Richard, but it's a highly reactive metal. It's sealed in this glass tube under argon atmosphere conditions, just for safety.
Right, so what's going to happen when you drop that in the water?
Well, imagine, if you will, letting off a hand grenade in a bathtub.
Righto, I'm off. Have that.
Okay.
Good luck. Okay, Tickle. Drop the rubidium in the water.
Stand back, everybody. This one's going to be bad.
2 grams of rubidium will only react when our specially designed vial dissolves in the water, which gives John a few crucial seconds to get into our safety zone. Yes!
Wow.
That is more like it. Only on Brainiac do you get that kind of science. But I believe we can go one better. There is one more alkali metal we can legally use.
Yes, Richard, cesium, the emperor of alkali metals, particularly nasty, could go off at any time.
And that's it.
Oh, yes.
Brilliant. I like it already. Now, what's that going to do when it hits the water?
Imagine a depth charge in a bathtub.
Fair enough, mate. I'll leave you to it. Good luck.
Thank you.
Okay, John. Go for it.
Warning, 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 extreme danger, clear the area.
As our cesium sinks in the water, the rapid generation of hydrogen gas should produce quite an explosion. And it does. Magnificent. And I think that concludes today's experiment. There is, I should say, one more, even more reactive metal, francium. But for some reason, they wouldn't let us have any of that. Still, there you go. Today's lesson.
Never mixed alkali metals with water.
All right, so as you can see, as we move down that alkali metal group, that group 1 elements, those explosions get extra big. So that means that as we go down, the reactivity gets stronger. Now let's go ahead and move on over to our alkaline earth metals, and let's kind of react them to water as well and see what happens. So here's a video of calcium metal with water. So as you can see, it's bubbling up, smoking, white foam starts. So it's producing a gas. And we'll learn about how we know that produces gas in chemistry B. So either trimester 2 or trimester 3 whenever you take chemistry B. So now let's go ahead and see what that, so it's calcium. Let's go ahead and go down to strontium, still an alkaline earth metals, but it's right below calcium on the periodic table. And see what happens when we react that with water. As you can see, it's still reacting with water. It's forming those bubbles. You have that smoke on the very top of the water. So it's doing the same exact reactivity. So that means all alkaline metals will react to water, but it produces more of a gas than an explosion. So let's go ahead and move on. And we're still going to look at the alkaline earth metals, but let's see, what if we light these metals on fire? So here's a video of me lighting up magnesium metal on fire. As you can see, it was a bright, bright, bright flame. It's kind of like a flare when I lit up magnesium. So let's go ahead and see what happens when you light up, burn calcium, which is right under the magnesium, and it's still an alkaline earth metal.
Calcium metal will also react rapidly with the oxygen in the air if it's heated. The calcium metal is flammable.
As you can see, it does the same thing. It was much brighter. So as we go down, they're still reacting with the oxygen, so that fire in the air, but it's going to get a much powerful light flame as we go down. So it's kind of like the idea of similar characteristics within those characteristic groups. Let's go ahead and kind of practice different elements and figure out what characteristic groups they're part of. Okay, so let's go ahead and look at oxygen. Now we know that so looking at the characteristic group, oxygen's highlighted as purple. So we know purple is nonmetals, so oxygen is a nonmetal. That's its characteristic group. Now let's go ahead and look at palladium. Now palladium is highlighted as yellow, and we know that yellow is our transition metals, so palladium is a transition metal. That is its characteristic group. Let's go ahead and look at francium. Now we know francium is highlighted as red, and we know that red is our alkaline metals. So francium is an alkaline metal. That's its characteristic group. Now let's look at ogdenus. OG, can't really pronounce that name. And that is highlighted as brown, and we know that brown is noble gases, so that element is a noble gas. That's its characteristic group. And then now we have europium. Europium is highlighted as black, so we know that that element is a lanthanide, and that's its characteristic groups. And that's how you'll figure out different elements and what group they're part of. And that's it. Thanks, guys.